Yeah, hello, class. Okay, so we're going to talk about flux and Gauss's law. And we're going to start out by defining flux for a, in general, flux would be just defined for a vector field. But we're going to, stick with just our electric field for now. Later we'll talk about magnetic flux, which is basically defined the same way. So let's say we have an electric field that's constant in some region. We're going to start with a simple case. So we have an electric field. I just drew one arrow for the electric field line. But again, here I'll draw a few more. It's constant in some region. So these are electric field lines. And say we cross a surface that has an area A. And for now, I'm going to define the flux to be E times A. The electric field times the area, or the magnitude of the electric field times the area. Now again, this is just a special case. We're going to kind of keep on refining this definition until we get to the most general case. So for now, we're just saying it's the electric field times the area. And the units, we'd have Newton meters squared per coulomb. So electric field is newtons per coulomb, area meters squared, our basic SI units. And so you'd think they would just give that a name, like we do to many other things, but as far as I'm aware of, there's no name for electric flux, so we're stuck with that. Okay. Now, intuitively, what is flux? Like, what does it represent? And intuitively, we can think of it as a measure of how many field lines are crossing this surface. Now, the problem is that that is a very imprecise statement, like the number of lines that are crossing a surface, because let's just say we have like a single positive charge Q. We can draw a picture to represent that. And again, I usually draw it like this with just 8 lines, but you can draw as many as you want. And so, the idea of like the number of lines associated with this electric field, that's a very imprecise statement. But intuitively, that's kind of what a measure of the electric flux is. And so let's complicate things a little bit now. Let's say we take that same surface with an area A and we rotate it. So that's its area A. But now we're going to get a smaller flux through this surface. Because if we stick with this kind of intuitive notion that it's a number of field lines that cross the surface, if we have, let's make a triangle here. Let's say this is a surface. Let's call this A perpendicular. And so this surface is perpendicular to the electric field, thus the name A perpendicular. And we can see like the same number of lines are going to cross through each of these two surfaces. So we might expect the flux to be the same through both. Again, kind of an imprecise statement. But you can see the flux has to be lower if we rotate the surface. Like if we rotate it 90 degrees, none of the field lines are actually passing through it. It's a mathematical surface with just like 2 dimensions that has no thickness to it. And so, the flux has to vary. It depends on the orientation with respect to the electric field. So let's just stick with this kind of imprecise statement that we're counting the number of field lines. And the flux through these two is the same. So what we're going to do is let's draw just one electric field. They're all pointing in the same direction because it's a uniform electric field. So they're all the same direction and the same magnitude everywhere in space. And what I'm going to do is I'm going to draw a normal vector. So normal, that is perpendicular to the surface. And let's say the angle between the normal vector and the electric field is theta. And so let's... Now, we can say, if we just say that we're kind of just defining it, so the flux through this surface is the same as a flux through a surface that would be perpendicular to the electric field. So they still block the same number of field lines. Then we can say the flux through our surface would be E times A perpendicular. But we just want to write it in a different form now. So if this angle is theta, that would make this angle theta as well. And this is a normal line here. And so this is a right angle with the surface. So if this angle is theta, this angle is going to be 90 minus theta, which would make this angle theta. So just from geometry, we can see that the angle between the normal vector and the electric field is the same as between that area and that perpendicular area. And so from this triangle, we can see that cosine of theta is A perpendicular over A. So we can rewrite our flux through this surface to be E A cosine of theta. And you might recognize this. It kind of looks like a dot product. And so we can define, let's redefine this normal vector. Let's define a vector A. So vector A is perpendicular to the surface, and the magnitude of vector A is equal to the area of the surface. And so then we can write the flux as a dot product of the electric field and that area vector. Another way you could write it is just leave the vector there, the normal vector, say E dot n and then multiply by the area. Just a little more compact to write it this way. Okay, we're not quite done with flux though, because we've been considering some very simple cases here. Like we have a constant electric field and a nice flat surface. But what if the surface is not flat? Or what if we have a flat surface, but the electric field is not constant? So an example of that, say we have a point charge. So the electric field lines go like this. They're radially outwards. And so if we draw a flat surface here, how do we calculate the flux? We can't just use that formula. And so what we have to do in this case, or similarly if we have just a constant electric field, but we had a curved surface, we're going to have the same problem. Let me redraw this. So here's our curved surface. And again, we couldn't even define this vector A for this surface because it's different at different points. Like the normal vector is different at different points on the surface. Here we can define a vector A. But again, taking the dot product of E and A, well again, the electric field has different orientations along the surface. So in both of these cases, we have the same problem. And so the solution to that is we break up our surface into small pieces. If you have any reasonable surface, if you break it up into small enough pieces, each piece is essentially flat. Just like, like the Earth, we have a curved surface. It's roughly spherical, but the Earth overall looks flat. Now, you might think it doesn't look flat because of hills and things like that, just irregularities on the surface. But you can't really see the curvature of the Earth from the ground. You'd have to be up really high to even notice the curvature of the Earth. And so the Earth appears flat locally, just because it's so big. And so again, whatever your surface is, if you break it up into small enough pieces, we can treat each piece as flat and then define a vector. Like here we have, say, dA1. Here's dA2, and so on. And at every point on the surface, we can draw the electric field at that location. And then we can find the flux through each piece of the surface. And of course, then to find the flux through the entire surface, we would add up all the pieces. And so when you break it up into pieces and add up all the pieces, what we are talking about is an integral. So the flux, we use this Greek letter as our symbol for flux. This is the definition of flux. And so we just define it that way. Kind of give you some motivation like why we define it this way, but that is the definition. And that applies to any reasonable surface. If you talk to mathematicians, you can come up with very unreasonable surfaces where it'd be impossible to define a flux at all. You could easily define a surface that is where you could not define a normal vector. There's actually an interesting example of a function that mathematicians, of course, come up with that is continuous everywhere but not differentiable anywhere. And you could generalize that type of thing and define a surface that just doesn't have any reasonable properties at all. But we're not going to bother with that. So without even defining what that means, just say like a reasonable surface, and we'll leave it at that. Okay. Now, one thing we need to point out here, though, is I just kind of said we define this vector A, or dA, if we're looking at a small piece of the surface, and I drew it like this, but I could have just as well drawn the vector the other way. And so we have a choice when it comes to defining, if we have a surface, we have this dA vector, we could draw it to the right. Here, let's say this is A1. But A2 would be equally valid. No reason to pick right over left. And so that's a problem. We want to be able to kind of uniquely define the flux without having this kind of disagreement about which way things are going to go. And usually, you just have to specify which way you're going to pick your A vector, your area vector. Now, let's say, but it's fine either way. Either way is valid. So let's say our electric field is to the right. So if we pick surface 1, where we define our area vector to the right, then E dot A1 is just E times A. Well, it's E times A1, but let's say, the area of that vector is equal to the area of the surface, so we just have EA. And if we look at E2, E dot A2 is minus EA. Because, the angle between E and A is 180 degrees. And cosine of 180 is -1. So again, in one case, if we pick our vector to the right, then the flux is E times A. If we pick the other way, then the flux is minus E times A. But that's fine because these are just two different ways of saying the same thing. So you just have to be clear about how you're defining your vector, and then there shouldn't be any problem. It's kind of like saying, let's say you move 3 meters to the right. You could just as well say you move minus 3 meters to the left. The result is exactly the same. And so it's just different ways of saying the same thing. You have freedom to pick a direction for your normal vector, but you might have to just communicate that information, although it'll probably be obvious anyways. Now there's an important case here, an important type of surface, and that would be a closed surface. So we can have a closed surface, and the flux through this is defined the same way. I'm going to write it down anyways. The notation is a little different if you're talking about a closed surface. You draw a circle around it, like around the integral symbol. And again, it's kind of optional. If you don't do that, it's not really a problem, because the person reading what you're writing should be able to see that it's a closed surface. But again, that's kind of standard notation if you have a closed surface. Now, there's one thing that's remarkable, and that, again, I mentioned that you can define your normal vector however you like. For a surface, there's two directions you could orient your vector that are perpendicular to the surface. But when we have a closed surface, we have an inside and an outside. And it's a convention, so now we have kind of this distinction. Before, for a flat surface, there's just two sides, but now we can distinguish there's an inside and an outside. And what's remarkable is that, as far as I'm aware, everybody in the math and physics community agrees that if you have a closed surface, your normal vector points outwards. And again, it's just a convention, and anytime there's conventions, people disagree, even though they're both valid. But usually some people will insist on just disagreeing, and that can sometimes lead to confusion. But nobody argues with this one. The normal vector points outside. Now I should make one point here that I said if you have a closed surface, there's an inside and an outside. And again, if you talk to mathematicians, they might disagree with you. And this picture on top, this is an example of something called a Klein bottle. And it might look strange because the surface kind of crosses through itself. And you might think that's not valid, but this is actually a perfectly valid mathematical surface. So it doesn't represent something physical, but we'll see a lot of times in physics, we get a lot of use out of defining surfaces that don't actually exist or don't represent physical things. And so a Klein bottle is a perfectly valid surface. The problem is it doesn't have an inside or an outside. It's kind of like a higher dimensional version of a Mobius strip. So like your Mobius strip, if you take a rectangle, like a paper, and twist one end and tape it together, that doesn't really have an inside and an outside surface. If you take a pen and just draw and keep going along the surface, you'll cover both sides. Unlike if you don't put that twist in it, you can take your pencil, go around until you complete a loop, and it'll just be like on the outside of the surface. Or you could do it on the inside, but without lifting up your pen, if you just go continuously around, you're going to be either on the outside or the inside. Same thing with a Klein bottle. It's a surface that doesn't have an inside or an outside. You can't distinguish them. And so again, we're just going to deal with reasonable surfaces. So, yeah, like some of the things we're talking about won't apply to things like Klein bottles or some other strange surfaces mathematicians come up with. We're going to deal with things like circles, or like spherical surfaces, cylindrical surfaces, or like cubes, things like that. We're going to keep it easy. And so then our normal vector always points outwards. So that's a convention that we all agree with. Okay, so we've defined flux. And again, this is just what it means now. So whatever we said, to motivate this definition, that's kind of irrelevant. This is just what flux actually means now, since we gave it a definition. And, kind of what is the purpose of flux? And this leads, we're going to use this when we talk about Gauss's law. Now, you might have heard of Gauss before. I hope you have. He's one of the greatest mathematicians of all time. He was also a physicist as well. He did a lot of work in all sorts of things, like obviously in math, a lot of very diverse areas like number theory. I think his most important work was probably in like complex analysis, and also one of the first mathematicians to work on something called non-Euclidean geometry. And yeah, he did some very important work there, and his student went even farther on that subject. His student, a guy named Riemann, which you also might have heard of, Riemann sums. But yeah, he did a lot of physics too. He was actually really interested in maps, things like that, and monitoring like the Earth's electric field. He was obsessed with mapping that out, and yeah, just all around very, very smart guy. Anyways, Gauss's law. I'm going to state Gauss's law. Let's do that. So what Gauss's law says is that the flux through any closed surface is equal to Q over epsilon naught. So remember, Ke is 1 over 4 pi epsilon naught. Yeah, the reason we have two constants, one for Coulomb's law and one for Gauss's law, is that this epsilon naught is more convenient for Gauss's law than it would have been. We could write, instead of epsilon naught, we could write 1 over 4 pi Ke. And so it's good to have both of these constants. But it's that same constant that we've seen before. Let's write down the value. So yeah, 8.85 times 10 to the minus 12 Coulomb squared over Newton meter squared. Okay, now this is Gauss's law. And it's not something that I'm going to prove. The book kind of proves it, but I don't like their proof, so I'll explain why. But here's what the book says. Let's start with that. So let's say that we have a spherical surface. Let's say we have a charge Q and a spherical surface with a radius R. And we can draw some electric field lines. Let's just draw one, actually. The electric field lines are radial. And again, this is a closed surface. We have to use this integral version of it. But if we look at this element of area, our dA vector would also be radially outwards from the center. So like any radial line is going to be perpendicular to the surface if that line passes through the center. And so there's kind of two things that happen here for this special case we're looking at, where we have our charge and a spherical surface that is centered on the charge. So one thing we can say is that E dot dA is simply E dA. Yeah, we also have this cosine theta term, just the dot product. We'd have cosine of theta. However, theta is the angle between the electric field and this area vector, and that is 0. They're parallel to each other. And cosine of 0 is 1. So our total flux is going to be the integral of E times dA. So again, we just have to break up our entire spherical surface and calculate this over each piece. But the other remarkable thing that happens here is the electric field at any point on the surface is going to have the same magnitude. So like here, this is the vector E. Here it's just the magnitude. And the magnitude is the same everywhere we're integrating over this closed surface. But E is constant because the electric field depends on the area. And so we can say that we can take that out of the integral, and then the integral of dA is just the area of the sphere, which is 4 pi r squared. Now the electric field is 1 over 4 pi epsilon naught. That's K, and then we have Q divided by r squared. So we plug that in, and a couple things cancel out. The 4 pi cancels out, the r squared cancels out. And so the flux is Q over epsilon naught. So you might think, well, we just proved Gauss's law, but we haven't, because this is a special case. What Gauss's law says is the flux through any closed surface is Q over epsilon naught. And so now we have to ask ourselves, what if we have a different surface? And I'll show you what the book does here. Let me clean this up a little bit. Let me just redraw this. So again, we showed in one case. Let's call this surface 1. And I'll draw a bunch of electric field lines. Center this a little better. So there's our charge. And so the electric field lines, we're assuming, well, we're drawing it as if it's a positive charge. So we've got all these field lines. And here's surface 1. Now let's say we draw surface 2, which is some irregular shape. So this is surface 2. Now what the book says is flux is just a way of counting electric field lines, and every line that crosses through surface 1 has to also cross through surface 2. And so the flux has to be the same. So yeah, if we can show that it's true in this one case, then it has to be true for any other surface, just because we're counting electric field lines. And I don't like that argument. I don't want to call it a proof because it isn't. And the reason why is, yeah, we're dealing with just electric fields here. And an electric field is a special type of a vector field. But this idea of flux is much more general than that. So let me give you an example. Let's say we have a different electric field. Or a different type of vector field. So instead of calling it E, I'll call it F for just some field. And let's say that's equal to C over R cubed. So this is the magnitude of this vector field, but otherwise it's just like the electric field. It's radially outward, so if you have some source, you know, the electric field lines would be radially outwards. And so let's draw a sphere with a radius R1. And again, we can use the same type of argument. And so we'd find the flux through this. And again, the normal vector. So we have some field line for this, this other type of field that depends on the radius cubed. And our dA would be, you know, so far the argument is just the same. Here's our vector field F. Here's this area dA. And the flux then is the integral of F. So again, we're just doing the exact same argument. And again, because it's a radial field, we defined it that way. This dot product is just going to be the magnitude of F times the magnitude of dA. And just like before, we can take F out. Because the function depends only on the radius. And every point on this sphere is going to have the same radius. So the magnitude of this vector function F is going to be constant, so we take that out. What we're left with is the area of our sphere. And so what we have in this case for the flux, that is going to be C over R cubed. Let's just call it R, we don't need this 1. Times the area, which is 4 pi R squared. And so here we have a constant 4 pi C. But now we have divided by R. And so the distance, the flux through this surface at a radius R, if we draw another surface, let's call this S1, and I'll put this R1 back. So the flux through surface 1 is going to be 4 pi C over R1. And the flux through surface 2, if we draw a spherical surface with a radius R2, call that S2, that's going to be 4 pi C over R2. So again, you can draw field lines for this function as well, and that argument would seem to hold up as well. Every field line that crosses surface 1 crosses surface 2, but that doesn't mean the flux is going to be the same. That's a special case that applies only to an inverse square law type of fields. So if you have any other function, that argument that the electric field, whatever lines cross through one surface has to cross through the other, that just doesn't hold up. It's a special case, and it does apply to electric fields, but again, we have not proven that at all. And it's actually kind of a difficult proof, so I'm going to kind of just move on and say, the flux, we showed that this result, which we're calling Gauss's law, the flux through a closed surface is Q over epsilon naught. We showed that for a spherical surface centered on the charge. But it applies to charges, it applies to any surface. And again, we did not prove that, and it's a very profound statement. That's Gauss's law. And he's the one that came up with, actually someone else I think came up with it before him, this other mathematician named Lagrange, who was one of the great mathematicians as well. I think he did more of a special case for it, but you know, whatever. They both kind of discovered it independently. But, okay, so that's Gauss's law. We're not quite done with it though, because we have to talk about what this Q is. So we have a surface, and Q is whatever charge is inside this surface. So let me give you an example. Let's say we have three charges. Q1, Q2, and Q3. And let's say Q1 is 6 microcoulombs, Q2 is minus 3 microcoulombs, and Q3 is 10 microcoulombs. So what is the flux through the surface? It's going to be Q1 plus Q2 over epsilon naught. So Q3 is outside, so like the surface encloses this volume, and that Q is just whatever charges are inside our volume. They're like inside the surface. And so Q3 is outside, we completely ignore it. And again, that is a very profound statement. Okay, let's say Q3 wasn't here. Or let's just get rid of Q2 as well. So let's say we calculate the flux with Q1 there. So what we have to do is we have to break our surface into like a billion pieces. All right, you get the idea. And the flux through this surface, I'm going to write it like this. E1, A1 plus E2, A2 and, you know, however many pieces we have. So, like, let's say this is area element 1. So, like, this one right here is A1. We have a certain electric field there. That would be E1. So, actually, these should all be dot products. But, yeah, so we do this. We take the electric field at a given location on the surface, take the dot product with the area vector at that little small surface there, and then we move on to the next piece and we add them all up. And we get some result. Well, we know the result. So again, that itself is a pretty profound statement that, you know, we can do this. We can see that the flux is just proportional to whatever charge is inside. Now let's say we place Q2 outside and we redo this calculation. So we keep the exact same surface. So now we do this, and again, these area elements are all going to be the same. Let's say we have like 1,000 pieces that we broke it up into, so we have 1,000 terms here. Now, if we place Q2 outside, every one of these electric fields is going to be different. And so every term that we add up is going to be different, but when we go through and add them all up, we're going to get the exact same answer as we had originally. And the reason why is it's going to make some of these terms bigger and some smaller. Like if we just look at one electric field line crossing our surface, here, like it's going to make this piece smaller because our area element is outwards and the electric field is inwards. And so, you know, when we get around to whatever piece this is, that term's going to be smaller. But then when we get around to like this piece over here, that piece is going to be bigger. And it's going to do so in a way that they just perfectly cancel each other out. So the presence of this charge outside affects the electric field everywhere on the surface. And so you would think that this would have an effect on the flux, but it doesn't. Any charge outside has no effect at all on the flux. So, yeah, that's a really remarkable thing there. All right, now we have Gauss's law. That's great. Kind of wish I didn't erase what I just had there, but you know, what good is Gauss's law? I'm going to kind of draw it again real quickly. There we have our charge Q. And again, the flux is going to be, we'll say, E1 dot A1 plus E2 dot A2. And so on. We add up a million pieces or whatever. However many pieces we break this surface into. Now the question is, we know the left side. We know that when we add up all this, this is going to be Q over epsilon naught. The problem is, this is one equation, and we'd like to know the electric field. Like say we have a charge here, we want to know what the electric field looks like. So the electric field, let's say, is unknown. Every term here contains an unknown. We have one equation with millions of unknowns. So as far as just using Gauss's law to calculate the electric field, it seems kind of like a hopeless task. However, there are a few cases where we can use Gauss's law to calculate the electric field. So that's one very important application of Gauss's law, that we can use it in special cases to calculate the electric field. But there's two things that has to happen in order to make this possible, that we can use Gauss's law to actually find the electric field. One is that the electric field everywhere along the surface has to be parallel to the area at that surface. Or maybe not entirely, maybe perpendicular would work as well, because that'd be zero. But that's one thing that has to happen. That we have to be able to deal with that dot product in a simple way. And the other thing is that the electric field has to be constant along the surface. So let's say the electric field is the same everywhere on this surface, and we don't need to distinguish E1 and E2 and so on, they're all just E. So if we can handle this dot product in a nice way, then we just have one unknown, and we can calculate the electric field using Gauss's law. And there's actually only a couple of cases where that's possible. I'll list the cases. We have a line charge, or let's say a cylindrical charge. So it could be like a line or a cylinder that's charged. And we can calculate the electric field using Gauss's law in that case. Another is a spherical charge. And another case is what we call an infinite plane. Now, can't draw an infinite plane. Run out of ink before that happens, so we'll just draw it that way. But, you might wonder what's the point of an infinite plane if they don't actually exist. And this turns out to actually be useful. We'll see that a little later. And I think what I want to do now is the spherical charge, that's really nothing new. It's the same as that point particle that we already did. So I want to skip that. I want to talk about the infinite plane. And I want to actually calculate the electric field due to an infinite plane in two ways. One using Gauss's law, and one just calculating the electric field from Coulomb's law. And then you might see why Gauss's law is important, because it's going to be a lot easier using Gauss's law to calculate the electric field due to an infinite plane. And so yeah, sometimes it can be useful for calculating the electric field. There's another special case where Gauss's law is very useful, and then is if we have like electrical conductors. And I'll talk about that later, like in a separate video, I think. But yeah, it can be very useful in that case as well. And another reason Gauss's law is important is because it is one of the fundamental equations of electromagnetism. So it's kind of equivalent to Coulomb's law. So what that means is you can take, you can accept Coulomb's law as being like your fundamental equation. That's based on experiments done by Coulomb, and using Coulomb's law, we can derive Gauss's law. Although we didn't do that, it's difficult, but it can be done. Gauss did it. Alternatively, we could start with Gauss's law and derive Coulomb's law. So in a sense, Gauss's law is equivalent to Coulomb's law. There is an exception to that, though, and that Coulomb's law is actually limited in a way, to where the charge is not moving. Because if the charge, like, just real briefly, let's talk about a limitation of Coulomb's law. It's not so much wrong, but in some cases, but we just have to be careful how we use it. Let's say we have a charge here, and Coulomb's law can give us the electric field at this point P. Now, what if this charge moves from here to here? Well, the initial electric field was pointing in this direction. After the charge moved, it's going to be let's call that E prime. So that's the location, that's what the electric field looks like after the charge moved. The problem is, what if I said this charge moved, you're at point P, what electric field do you see? You're still going to see this one for a little while at least, because the information that this charge moved, you can't know that the charge moved until the information reaches you, and information cannot travel faster than the speed of light. Now, that's usually pretty fast. It's like if the sun just disappeared right now, we wouldn't notice anything different for about 8 minutes, because that's how long it takes for light to travel from the sun to the earth. So we would still see light for 8 minutes. And we would still feel we'd continue our orbit like nothing had happened at all, because the gravitational field would not be affected by the sun disappearing until that information can reach us. So Coulomb's law kind of has to be modified a bit if you want to take that delay into account, which can be very important. Gauss's law doesn't have that issue, so yeah, it's in some ways considered more fundamental than Coulomb's law. But otherwise, they're equivalent, so most cases they are. So I think what I'm going to do is I'm going to end this video here, and I'm going to have a separate video where we're going to calculate the electric field due to like an infinite plane of charge using Coulomb's law, and then we're going to do it with Gauss's law and see that one of them is much easier than the other. But I'll do that in a separate video.